Left 5 falling slinky. The purpose of today's video is to predict and measure the motion of an elongated slinky when dropped from rest. To make this easier for us, we will visualize the slinky as an extended system through VPython and Tracker. Next, we will plot the position time and velocity time graphs. The main lab results we will see by the end of this video is 1. The slinky as a point particle falls at constant acceleration, and 2. The slinky as a multi-particle system falls at different rates. So in other words, the point at the bottom of the slinky stays motionless for the first few seconds, whereas the center mass just falls straight down. The main physics ideas that are present in this experiment are Newton's second law, F net equals dp dt, gravitational force, F equals mg, drag force, Fd equals negative b, which is the air drag constant, times velocity squared times v hat, and slinky tension. We also use the energy principle to model the extended system, and of course we need the velocity update and position update equations for our code and models. In this experiment, I downloaded a video of a person dropping a slinky of approximately 0.22 kilograms from rest. The top of the man's hand to the floor is approximately 1.8 meters, and the slinky fell in the negative y direction. I tracked 2 different videos in Tracker. The top picture displays the center of mass being tracked, while the bottom picture displays the bottom of the slinky being tracked. The initial conditions for the extended system, the bottom picture, is positioned at negative 1.27 meters in the y direction. Velocity is at rest, initial time is at 0 seconds, and final time is 0.467 seconds. The system is a slinky, and while the surroundings include the Earth and the atmosphere. In the first part of the code, I simply outlined the initial conditions I already stated: mass, position, velocity, and drag, which I set to 0.5 through trial and error. Next, I implemented 2 while loops to support 2 conditions in my experiment. In the first loop, I calculated the net force on the slinky in the first 0.2 seconds while the bottom of the slinky was motionless. At this moment, all forces cancel out and they result in a net force of 0, which explains why the bottom of the slinky is motionless. In the second while loop, I calculated the net force again, but this time it's after the 0.2 seconds. The calculation is the same, except this time the slinky tension force is 0 because the slinky is fully compressed. So the slinky is not exerting any force towards the system. Additionally, I used position update and velocity update equations to plot the location of the slinky. When obtaining data from Tracker and VPython, I modeled this graph to compare the different curves. It turns out that the graphs share the same trend. The graphs are flat in the beginning because the slinky is motionless. Next, they begin falling at the same time, and they fall at roughly the same distance. Curve 1, the computational model, is much smoother because this would be a perfect example of what would happen. Curve 2, on the other hand, is the experiment curve, and it's much more jagged. The system even goes up a little before falling. One explanation for this discrepancy is a misplacement of dots when using Tracker. Now, what if we analyze the center of mass? We will see that the center of mass accelerates as usual. In the previous examples, the system was motionless for the first few seconds because we were tracking the bottom of the spring. In this example, I tracked the center of mass, and it turns out that the external forces of gravity and air drag affect the slinky just like any other system. That's why on this graph, you can see that acceleration of gravity is the same as any other object. What about the real system and the energy principle? We can find delta K translational by calculating the work done by the net forces, excluding the slinky because it is part of the system. This case is similar to the GPS spring problems we have seen before, like in the picture below. That's why we don't include the slinky tension. But in delta K relative, we calculate the work done on the system as separated forces. This calculation does include the force of the slinky. Therefore, we can say that relative kinetic energy is dependent on the work done by the slinky. In conclusion, we can visualize this experiment as an extended system problem. The center of mass falls at constant acceleration, while the bottom of the spring remains motionless for some time. The point particle falls normally, while the multi-particle falls differently. Some potential sources of error include the tracking that could be inaccurate while placing dots, friction of the slinky was not accounted for, and the initial conditions such as position and slinky weight could be off because I just took them as the average position and weight of slinky.